Hi everyone, my name is Aline Montenegro, and here I'm going to talk about the project that I developed during this internship experience, along with my mentor, Ginny, entitled SKS Splitting in Cascadia. So this is a little outline of what you should be expecting to see in this presentation, and the first part of it, here are some of the goals, the main goals of this project, which are to better understand the anisotropy phenomenon happening at subduction zones, to learn how to use pitch racer routine to measure SKS splitting, and to explore SKS splitting measurements on nodal arrays, and also to identify subtle along dip variations in SKS splitting measurements in subduction zones, in this case, the Cascadia subduction zone. And to do that, we analyzed data from two experiments, the XG from 93 to 94 and the ZO from 2017. So a little science background on this topic. Seismic anisotropy, it is a property that some minerals have caused by stress processes happening inside the Earth, mostly due to asthenospheric flow. And when this happens, it causes the splitting of shell waves going through them. And during this process, we have two parameters, which are phi, two parameters that we're going to use, which are phi, the angle between the fast axis direction and the east-west direction, and delta t, which is the time interval between the slower component and the faster component of this wave. And the region we are studying, it is the Cascadia subduction zone in western US. In this region, we have the Juan de Fuca plate, a remnant of the Farallon plate, being subducted by the North America one. And during this process, we have not only mantle flow going downward the slab, but also around it. And this is expected to cause a rotation of fast axis directions. And we're going to see better how it affects the results that we got. So the methodology, we use the speech racer routine, which is a MATLAB code used for analysis and interpretation of shell wave splitting, and it was based on the method of transversal component minimization developed by Silver and Chan in 88 and 91. So the results we got, for data acquisition, we used the data catalog of GMAP and Wilbur3 from IRIS. To download the data, we used OpSpy. To do the processing and analysis, as I just mentioned, we used SpeedRacer, and to plot the results, PyGMT. So the experiments, as I first mentioned, they are the XZ network and the ZO network, both in the state of Oregon. So the results we got for the first experiment, this is a larger array, as we can see, but a smaller one in the matter of number of stations. But still, we can see a little rotation, a slight rotation in the fast axis directions of the splitting we got. And when we move to the results of the second experiment, we can see that even though it is a smaller array, it is higher in the number of stations. It is much higher than the first one. So in that way, we can see much better the way that the rotation happens in the fast axis. So in a way that it gets almost perpendicular to the east-west direction. And because of this, we have a mean value of phi higher than we got for the first experiment. And also we get a DT value smaller than the first one, probably because of the type of array. This is a nodal array. And because of this, we have short period sensors that will probably cause the DT to be different from the first one, along with other causes as well. So with these results, we were able to see clearly the rotation of the fast axis, indicating that we have in this region a trench parallel flow direction of the mantle, as we were expecting. So about my experience during this internship, the main learnings that I got are how to better use the IRIS web services provided, and also how to better manipulate and manage them using SAC and GMT. This is what was really important for me. And also I was able to better understand the career and the areas I'm able to explore as a researcher in geophysics. So at last, I would like to thank the whole EarthScope team, the whole team of coordinators, Molly and Justin, for allowing me to live this experience, for allowing me to live this opportunity, and to have this whole new perspective on researching on geophysics, and also the whole team of graduate students who are there for me and the other interns, and also the whole team of interns, just like me, that were in this program. And at last, I want to thank my mentor, Jeannie, who has been such a great mentor and really was the best one I could ask for because she has experience in the two areas that I love the most, which are seismology and geodynamics. And so I was able to work in this project and have this whole new perspective on how I can use SK splitting to better understand the dynamics inside the Earth. So really, thank you so much, everyone, for this opportunity. And this is it. Thank you so much.
Hi everyone, my name is Paula Alondra Guerrero, and today I will be presenting all about my participation in this year's internship. I was very lucky to collaborate with my mentor Abhigyan Chatterjee in this project called Using Local Earthquake Shear Wave Anisotropy to Quantify Stress Changes Over Time. So the content of this presentation consists of the introduction, the objectives, methodology, results, and references. So to begin with, I find it really useful to first understand what we talk about when we talk about seismic anisotropy. Seismic anisotropy can be defined as the directional dependence of the velocity of seismic waves in a medium within the Earth. It can be caused by multiple factors such as preferred mineral orientation, presence, and abundance of fractures and faulting, orientation of regional tectonic stress, layering of sediments, etc. To measure it, a process of shear wave splitting can be used. So shear wave splitting is a phenomenon in which a shear wave, when passing through an anisotropic medium, is polarized into two orthogonal components that travel at different speeds. So when the wave reaches a seismometer, the delay time between the fast and the slow components can be measured. The angle between the incident wave and the polarization of the fast component is called the fast direction, and it can also be measured. So both of these parameters, delta t and phi, can be used to relate the information about the degree and orientation of anisotropy. It's important to mention that the observations of the fast propagation direction are really useful for inferring the stress orientation in the shallow crust, as well as the flow regime in the mantle. In this case, these observations were used to determine the maximum horizontal stress direction in the San Jacinto fault zone. So any changes in anisotropy that are detected over a short time scale or a short period of time can be attributed to changes in the stress field location. Therefore, by measuring changes in seismic anisotropy over time, it may be possible to quantify changes in stress near a fault or a fault zone. This leads us to the objectives of this project. So the overall objective of this project was to determine whether stress changes can be detected using shear wave splitting measurements along the San Jacinto fault zone in Southern California. This by analyzing earthquake data collected between 2008 and 2020. In addition to this project was also assessing the question of how the changes in anisotropy can be linked to the observed seismicity and strain data. So moving on to the literature, this is a list of the literature I was assigned to review in order to have a deeper understanding about shear wave splitting and anisotropy and the conclusions we can draw from these measurements. So I'm not going to explain each and every one of them because it would take a long time, but I would reference everything in the last slide so you can access it if you are interested in this topic. So this is a little question that I put here, the why the San Jacinto fault zone. So this question popped into my mind a lot of times, I was asking myself, why did they choose the San Jacinto fault zone to do these measurements? And the answer was that this region in particular has a very dense station coverage, and this allows for a good quantity of measurements to be done and to pick from. So a brief description of the methodology that I followed in order to complete my tasks. So the clustering of events I didn't do, but I did have the list of the clusters that had the events within that cluster with the event ID. And then, well, once I had this, I also had the list of data that I had to download from the STP program, which I also downloaded into my computer. And then once I downloaded all the requested data, I executed a Python base code to ensure I had all the necessary information for further analysis. So this further analysis was to run another Python base code that did the actual shear wave splitting measurements. And this is where my particular tasks come in, which are, well, consisted mainly on the quality control part of the project, which was to run this code. And with each plot, I had to grade the measurement based on this flowchart here. And I had to pick the quality level that ranges from 0 to 3, 0 being a bad pick or a bad S window, and then 1 is a poor quality measurement, 2 is a medium quality measurement, and 3 is a high quality measurement. So I went ahead and put an example here of one of the measurements for one of the stations and one of the events, because it was done as event station pairs. So this particular example was graded at a 3, a high quality measurement, due to following this flow chart here. So the S peak was reasonable. It didn't have more than one contour. The R squared was a high value, and the uncertainty was a low value. And so following this, we went ahead and followed this like a flow chart, like a path that led us all the way to a number 3 measurement. There were a few exceptions with some of the measurements, but overall this was the main guide for the grading. So for the results, I don't actually have the results, but some preliminary results were that there's a radial decrease in anisotropy, which implies that most of the anisotropy sampled by the ray path is located near the damaged, highly complex main fault zone. So that is it for my presentation. In my particular experience, I really enjoyed the whole process, and I found it really helpful. And not only the workshop, but the project as well. I mean, I learned how to use the different tools available for seismic data analysis, and it really opened up a whole lot of new opportunities to do some more research in regards to the anisotropy topic, and some other research topics. I mean, the tools are amazing. The coding was extraordinary, and it really makes me excited for the future and for my personal professional career in this field. So thank you very much. Thank you very much for the opportunity to participate in this internship. Thank you for the space given to me to share and learn with all of my peers and my mentor. So thank you very much.
Hello everyone, my name is Roberto, and today I will talk about my research project for the IDSC internship. which is titled Frequency Characterization of Volcanic Tremor Signals Preceding the 2019 Fakari Volcano Eruption. So, what is a Fakari? Fakari, or White Island, is a stratovolcano located north of the Bay of Plenty in New Zealand. It is New Zealand's most active cone volcano and is predominantly made of andesite. Fakari is important because of its notoriously violent eruptions, such as the one that happened on December 9, 2019. This eruption claimed the lives of 22 tourists and injured 25 more. Tours were on the island because there were tours that were usually carried out, but the island is not inhabited. Before the eruption, a series of volcanic tremors and an increase in sulfur dioxide levels took place, which was noted by the Volcanic Activity Bulletin of New Zealand. So the objectives of this project were essentially gaining an understanding of volcanic tremor signals and comparing those signals against others from different phenomena, which may include regional earthquakes, smaller local earthquakes, and so on. In particular, the sequence of tremors that I analyzed began 2 to 3 weeks prior to the eruption. I sourced the data from 2 stations that were present at the time at Fakari, which are WIZ and WSRZ. These stations are no longer active there, but I managed to download a month's worth of data from both, which covered both the pre-eruption tremors and the eruption itself. And we can see the location of those stations here on the map. So as for data processing, OSPI was the main tool that I used, but I also used custom routines from NumPy and SciPy that I wrote for some frequency analysis. The instrument response was usually removed except for probabilistic spectral density plots, where the OSPI routine already takes care of that. And whenever I had to do frequency analysis routines, I first detrended the signal using a third-degree polynomial spline with a length of 500 samples, that is 5 seconds, according to the sample rate of the data. And as for the filters go, for frequency analysis, I applied a high-pass filter with a cutoff frequency of 0.05 Hz to eliminate the long-period contributions to the signal. And for the RSM data, which I obtained from Craig Miller, a research at GNS in New Zealand, the data was filtered between 2 and 5 Hz with a bandpass filter. So, for the frequency analysis, 3 frequency parameters were calculated. The central frequency, which is based on an average frequency where most of the power is concentrated, the median frequency, where half the power has been accumulated up to that point, and peak frequency, which is, strictly speaking, the frequency with the highest amplitude of all after computing the fast Fourier transform. So here are the results. Let's talk about the PPSD first. We can see 4 different cases here. One is a local earthquake at the beginning of the sequence. The second one is the 5.9 moment magnitude, an earthquake that happened on November 24th. And the other 2 cases are resting periods between tremors, which are called troughs according to the RSM data, and volcanic tremors, which are called peak, which can be seen as peaks in the RSM data. We can see that the frequency content for local earthquakes tends to be higher than even the resting periods. Frequency content for the November 24th earthquake tends to be lower, and the range between resting period peak frequencies and volcanic tremor peak frequencies tends to be narrower. Let's look at the frequency analysis. So we can see a consistent pattern for most of the RSM peaks, which is the graph shown in light gray color. Central and median frequencies tend to decrease whenever a volcanic tremor is present, only to jump right back up after that tremor is done. However, there is an RSM peak that has a noticeably higher frequency parameters, which corresponds to a small local earthquake. So, as for conclusions and takeaways, we can see that a consistent pattern of frequency content changes was demonstrated for volcanic tremors. Usually, some frequency parameters, which may include median and average frequencies, tend to decrease their value with tremor activity, only to go back to normal after the tremor is gone. These patterns may then be applied to characterize the frequency content and nature of other tremors, especially tremors that might precede a volcanic eruption, aiding other volcano activity monitoring techniques. So, my personal takeaways for this internship were increased aptitude for seismological observation and processing, especially related to volcanic seismology, which is what I want to pursue as a grad student. Also, I gained more confidence in using code for tackling different problems, maybe not only for seismology, but for other disciplines that require massive management of data, and also more teamwork skills. So, thanks for tuning in. It was a pleasure working with everyone here. Muchas gracias. Hasta luego.
Hello, my name is Oyugi Kerubo Maurine from Jomo Kenyatta University of Agriculture and Technology, Kenya. I was conducting a project on analyzing GNSS data and earthquake catalogs in Oklahoma to understand signals related to induced seismicity and reservoir deformation. My mentor was Dr. Junle Jiang, an assistant professor at the University of Oklahoma. My co-mentor was Shegan Bodunde, a PhD student at the University of Oklahoma. Anthropogenic activities in the subsurface have resulted in induced seismicity. Some of these activities include geothermal energy extraction and wastewater injection. In the US, the oil and gas industry is the leading contributor of the Earth's subsurface interference, considering that they inject approximately 4 barrels of wastewater for each barrel of oil. This image is an illustration of a wastewater well for the oil and gas industry. Oklahoma State is experiencing induced seismicity of magnitudes larger than 5 since 2011, and there have been 4 of such events. Pony earthquake of magnitude 5.8 in 2016 is the recent one with the highest magnitude recorded in the region. The large magnitude earthquakes are causing hazards such as structural damage and even a rise in public safety concerns. For instance, this is an image indicating a road that was damaged by an earthquake. Therefore, studying aftershocks of large earthquakes is essential to aid our understanding in signals related to induced seismicity and even in predicting future events. The general objective of this study was to understand signals related to induced seismicity and reservoir deformation. Our specific objectives were to analyze earthquakes from 2010 to 2023 in Oklahoma, to investigate the Pony 2016 magnitude 5.8 aftershocks, and to evaluate potential signals related to induced seismicity and reservoir deformation using GNSS data. Our study area was Oklahoma, Pony County. Our general methodology was that we collected a shapefile from data.gov and earthquake catalogs from Oklahoma Geological Survey. The catalogs were filtered using depths of less than 14 kilometers and magnitude more than 3, and we also filtered our location to Oklahoma. Afterwards, we visualized our data using the years, the magnitudes, and the depths. We then focused onto Pony, where we also visualized our data using the years, the magnitudes, and the depths. For the GNSS data, we got it from Nevada Geodetic Labs, which we then detrended using the common mode error. We denoised it using the median filter and visualized it using combined plots for each component in each station. The output from the two procedures was used in trend analysis, whereby we evaluated GNSS signals and compared them to earthquake catalogs. Our results indicate that Oklahoma is experiencing a lot of seismic activities, and most of these are in the northern and the eastern region. These events are mostly between 2013 to 2019 with depths of majorly between 4 and 8 kilometers. Zooming into Pony, we see that mostly the magnitudes are between 3 and 4, and the depths are between 4 to 8 kilometers. This is not very different from the whole region of Oklahoma. Focusing on the aftershocks, we see that the large events are mostly near the 2016 magnitude 5.8 event, and their depths are mostly between 4 to 7 kilometers. It should also be noted that after early 2019, there are no major aftershocks in the region. This is a screenshot indicating the aftershocks of the Pony 2016 magnitude 5.8 event that is illustrated using the big circle, and then the others are the aftershocks. So we see that in 2016, there are aftershocks that are displaced, like they are everywhere on the Pony region, while in 2017 we see that they are decreasing and they're majorly a bit far away from the 2016 magnitude 5.8 earthquake. In 2017, we see that they also decrease and they are quite far away. But in 2019, we see that they are now starting to occur closer to the magnitude 5.8 earthquake of 2016, and specifically the closer one is of magnitude 3.8, which is significantly big. This HTML can be interacted from this attached document. For the GPS data, we see that there is a lack of post-2016 signals after the Pony 2016 main shock in all the components, that is the east, the north, and the vertical component. However, there is a transient signal in early 2019 indicated with the red arrows in all the components, and this may be associated with the magnitude 3.8 event that happened around this time. It may also be caused by a seismic creep, considering that between 2019 and after 2019, there were no major aftershocks in the region. A reduction in displacement in the eastern component may indicate that there is a stress redirection that may be towards the northern component, considering that there is an increase in displacement in the northern component after 2019. An increase in the vertical displacement of after 2019 may also indicate or signify that the area is experiencing reservoir-related deformation. One station is an outlier that it has large fluctuations in all the components, and this may be caused by local conditions. These are combined earthquakes and GPS observations, whereby the squares are the GPS stations and the circles are the earthquake events. The arrows are the displacement, whereby the red arrows are the vertical displacements, while the mustard arrows are the north displacement. The down vertical arrows indicate that this is a negative displacement, while the up vertical arrows indicate that this is a positive displacement. Therefore, we see the stations such as 06 and 07 and even 08 are experiencing a down displacement, which indicates a subsidence, while stations such as 04 and even 01 have an up arrow indicating that they are uplifting. This is an indication, therefore, that this region is divided into two sections, and we estimate the fault using these blue dotted lines. However, we notice that 04 is coming to this other side, and practically we know that a fault cannot be a straight line, so we draw a line to distinguish or to separate so that 04 is to its correct section. For the north displacement, for instance, we see that stations such as 06 and 07 have an up arrow indicating that they are moving towards the north, while stations such as 08 and 01 have a horizontal arrow indicating that they are quite stable. Therefore, we also see that this region is divided into two regions, and we estimate our fault using the green line, the green dotted line. We notice that these faults are intersecting near the Pony 2016 magnitude 5.8 earthquake, and this observation is consistent with other studies such as the Chan et al. 2017. This study concludes that seismicity in Pony is decreasing as there is a reduction in large events. However, the region's faults are active, experiencing horizontal and vertical displacement. The intersection between the two faults, the fault planes in Pony, may therefore contribute to future seismic events. This study recommends that future research can explore injection history to determine the cause of the surface shift observed after 2019. Thank you.
Hello everyone, I'm Sheikh Sazzad Mahmud, currently studying at the Department of Geology, University of Dhaka, Bangladesh. I would first like to thank the 2023 EarthScope IDSC Internship Committee for giving me the opportunity to work on this project. And I'd also like to acknowledge my mentor, Lin Chao-hee. Without her help, I couldn't have learned as much and couldn't have completed this project. The project for my summer internship was 3D modeling of explosive event in Cascadia subduction zone using pilot. So what is a explosive event? A explosive event is a gradual and slow periodic release of tectonic stresses. It is also known as silent earthquakes. Explosive events can significantly impact the mega earthquakes on the region by accumulating stress and creating a stress storage area and then releasing it on tectonic plate boundaries. Cascadia is one of the major subduction zones where we can see intense slow-slip tremors. It extends for about 1,300 kilometers from northern California to southern British Columbia. It is the convergence between the two plate boundaries, the Juan de Fuca plate, which is subducting beneath the North American plate. The main platform for our simulation and modeling was Pilot. Pilot is a finite element simulation software created by computational infrastructure for geodynamics, who are still now actively developing this program. The parameter by which Pilot's material property are defined and calculated are given over here. Our modeling can be divided into three parts: the mesh generation, the data collection, and the simulation of the specific event. The mesh generation, for this we used a software called Qubit, where we created a nerve surface using the three-dimensional Cartesian coordinate vertices inside Qubit, which were geographically referenced for Cascadia subduction zone by the study of ISET et al. Then we generated our whole mesh block. The whole block's dimension is given over here, but our simulation is not going to be occurring throughout the whole block, so we created a deformational block. The dimensions for the deformation block is given over here. The key components from this were the subjecting slab top, slab bottom, and the slab splay fault. Then we imprinted our rupture patches of the whole block, the deformational block, and the splay faults. And then we generated node set along which the tetrahedral polygons were generated for our mesh, and then ascribed material properties within Pilot, and finally we generated our tetrahedral mesh. Before data collection, we had to identify a explosive event, which we identified from Pacific Northwest Seismic Network, which was from July 15 to August. Then we evaluated the resultant data and then calculated accumulated slip. The explosive simulation, for this, we had to first generate a configuration file to enter our data. Then we had to run our configuration file using a Python script and convert our configuration text data into another Python script. And then we have to execute a prescribed explosive configuration file named step6 config file, which was prescribed in PyLib. And then we have to define the properties for the parameters which are prescribed in PyLib, which in turn generated 13 files with extension of .h5 and XML. Then we ran these files onto the paraviewer program. This is the config file where we enter our data, the sleep rate, the sleep center, sleep maximum, the sleep amplitude, sleep times, etc. And this is the file where we have defined our simulation process with the total time and time interval. This is the view of paraviewer, and this is the file that we ran for our displacement work. And finally, we got our result. This is our simulation. From here, we can see the red zones are where the maximum displacement occurred, and the blue zone is where there was little to no displacement at all. The maximum displacement was 1.2 into 10 to the power minus 38 meter. So the results we got from this was the maximum sleep, which is 0.059 meter. And it was found on the 16th data point, which gives us the date for this maximum sleep was 22nd July 2023. Then we calculated the maximum sleep magnitude, which is 1.2 10 inverse of 38 meters. Then we calculated the results. Then we calculated the results of our sleep direction, which was 235 degrees, which matches with Drager's previous study. Then we saw the stress warping, and the picture below shows us the vertical displacement for this slow sleep event, which is showing the maximum vertical upliftment of 1.2 meter, maximum vertical subsidence of 0.69 meter, and the sleep rate is 0.0375 meter per day. In our conclusion, we identified some crucial parameters such as the vertical displacement and the sleep rate. Then we confirmed Drager's sleep direction of Cascadia subduction zone. Then we saw the upliftment along high stress zone and the subsidence along the adjacent area. The periodic nature of slow sleep event makes the upliftment and subsidence also periodic, which makes the adjacent area more vulnerable to many dangerous hazards. Our model has a capability to predict the future slow sleep event, which in turn could predict the future earthquakes. By incorporating the findings of our modeling and simulation with the previous data, we can see that the varying rate of seismic sleep could cause complete relief of deep coupling, which in turn could generate a mega earthquake in Cascadia subduction zone. Thank you very much for August 1st.
Greetings, everyone. My name is Aian, and I'll be discussing the frequencies shaping or controlling ground motions in the San Francisco Bay Area. So, for starters, I want to briefly discuss what affects ground motion. There are three main components that control ground motion. The first is the source. The earthquake source is where the seismic wave is generated and is characterized by its magnitude. Larger earthquakes release more energy, leading to stronger seismic waves and greater ground shaking. Apart from magnitude, other source mechanisms such as depth and type of faulting could also affect the wave frequencies and amplitudes of ground motions. The second is the path that the seismic waves travel through. As the seismic waves travel further away, they are spread out over a larger area, so the energy density decreases. In short, seismic waves lose energy or attenuates as they travel through the crust. And lastly, the focus of this project, the site. Depending on its geology, the site can attenuate or amplify the ground motion, leading to a varying intensity levels of shaking at different sites. There are two parameters specifically tackled in this project. First is the VS30, which is the time average shear wave velocity in the upper 30 meters of the crust, and the kappa, which describes the local attenuation of high-frequency ground motion. Seismologists often aim to estimate the anticipated shaking resulting from an earthquake in a specific region, as this information shapes national hazard maps and building codes. Typically, we make these estimations using ground motion models, or GMMs. These models predict various intensity measures, such as peak ground acceleration, or PGA, and peak ground velocity, or PGV, based on factors such as earthquake magnitude, distance from the earthquake source, and local geological site conditions. We commonly associate peak ground acceleration with higher frequency seismic waves and PGV with moderate or low frequency seismic waves. However, local site conditions can both amplify and attenuate seismic energy across different frequencies. While various studies have individually explored the effects of amplification and attenuation, they rarely examine the phenomena together. So, for this project, our study area is the San Francisco Bay Area. We aim to evaluate which seismic frequencies PGA and PGV occur at for a large data set of recording in the San Francisco Bay Area, and compare these frequencies with different site conditions to see if the frequencies are site class dependent. The study conducted holds significant importance in the field of earthquake engineering and ground motion modeling. By discerning the specific frequency ranges that govern the PGA and PGV, engineers gain a deeper insight into the mechanics of seismic events. This understanding enables them to formulate more effective strategies for designing structures that can resiliently withstand earthquakes. Moreover, the studies focus on unraveling the intricate connection between the frequency ranges and site conditions contributes to a fundamental advancement in refining ground motion models. This refinement directly translates to heightened accuracy and precision when predicting how ground motions will propagate during seismic events. In order to achieve our objectives, we have utilized this methodology. First is we gather the data by downloading and processing the waveforms using GM process. Then, we proceeded with the coding phase, utilizing Python for the project. Notably, we employed a set of frequency ranges instead of determining the precise frequency values that control the PGA and PGV, which simplifies the approach. We iterated throughout our dataset, applying multiple filters to the data. For instance, we utilized a low-pass filter for frequencies below 1 Hz. Our goal was to identify which frequency range filter would yield a PGA or PGV value equivalent to the unfiltered data. However, this task proved to be challenging, leading us to opt for the filter that provided the closest value to the original PGA or PGV. The selected filter was then designated as the controlling frequency range for these ground motion parameters. Naturally, we didn't create the script flawlessly in a single attempt. The code went through multiple debugging processes, which actually consumed a significant portion of our time during the project, as we were striving to identify the issues in our code, as well as try to fix these issues. Fortunately, we have completed the step successfully by developing a functional script for our project. Lastly, to facilitate the visualization and analysis of the data, we created plots. Specifically, we employed seaborn.stripplot in Python, considering that each of our stations encompassed multiple data points, and there was often overlap among the values in our dataset. Following the plotting process, we proceeded to examine the graphs and to identify any correlations among our variables. So, here are our results. The initial plot presented showcases a comparison between the frequency ranges governing PGA and PGV against the VS30. To begin with, the plot distinctly illustrates that PGA, which is marked as blue points, is primarily impacted by higher frequencies, while PGV, marked by orange points, is predominantly influenced by lower frequencies, which aligns with existing literature. However, an evident correlation between the frequency ranges and VS30 isn't readily apparent in this graph. The same observation applies to the graph depicting frequency range versus kappa values. Once again, the plot distinctly portrays that PGA is primarily influenced by higher frequencies, while PGV is mainly responsive to lower frequencies. However, a definitive correlation between the two parameters remains elusive. Based on our findings, a strong connection between frequency ranges and the site parameters kappa and VS30 doesn't appear to exist. Consequently, we began exploring other potential factors contributing to the frequency ranges, potentially the source or the propagation path. But given the complexity of investigating the propagation path within the remaining time, we chose to explore whether the site characteristics, particularly the magnitude, could be contributing factors. So, given the use of similar stations as with the other graphs, the frequency ranges governing PGA and PGV remain consistent. As for the connection between magnitude and frequency ranges, a distinct correlation is again not readily apparent. Firstly, noticeable gaps exist along the x-axis of the plot, representing magnitude ranges with no recorded instances in the area. This could potentially create a misleading association between two involved parameters. Secondly, the dataset scope appears insufficient to establish a significant correlation between the two parameters. Expanding the dataset's domain could, or to include larger earthquakes, would likely yield a more meaningful interpretation. Another aspect we explored involved examining a new dataset, distinct from the previous one in terms of the way the data was processed, but derived from the same stations and events. This examination aimed to identify any disparities in the data. Surprisingly, the new dataset yielded peculiar results that significantly diverged from the outcomes obtained using the earlier datasets. As we'll delve deeper into the investigation, it becomes apparent that the PGA and PGV values from both datasets exhibited substantial differences. In particular, we uncovered that the older datasets contained notably higher PGA and PGV values compared to the new dataset, with differences approaching nearly 2 orders of magnitude. This helps us understand that the problem is more complex than we initially thought, because there are more factors contributing to the peak ground acceleration or peak ground intensity measures besides just the site or source conditions. In conclusion, a strong correlation between the frequency ranges that govern the PGA or the PGV and the site and source parameters is not readily apparent. Recommended future work related to this project includes investigating path parameters, like regional crustal quality factor Q. Researchers may also examine how the azimuth from the earthquake corresponds to the frequency ranges that impact ground motion using GMT or other mapping tools. Moreover, additional datasets from different regions can be explored to identify any potential correlations between strong ground motion parameters and frequency. So this summer, I achieved a significant milestone by acquiring coding proficiency in Python. Despite my limited prior experience with the programming language, I dedicated time and effort to learning Python, allowing me to effectively load or code and solve problems, especially within this project. Furthermore, I expanded my skill set into the realm of seismological research. While I had previously conducted research before, this summer marked my exploration into seismology, a field I had not previously delved into. Through focused efforts, I developed valuable research skills within this domain, contributing to our project and enhancing my understanding of seismic phenomena. So, thank you so much for listening, and that's it.